Have you ever stopped to think how your phone can just instantly show you the 50th photo in your gallery? Or how a social media feed can load hundreds of posts all in a perfect line? Well, the secret is often a super simple but incredibly powerful data structure called an array. Today, we're going to pull back the curtain and see what really makes it tick. All right, here's our game plan for today. We're going to start with a fundamental trade-off that every programmer has to wrestle with. Then, we'll dive right inside the array itself to see how it's built. After that, we'll uncover the hidden cost of making changes, learn a crazy fast trick for finding things, and wrap it all up with a simple cheat sheet that tells you everything you need to know. You know, anytime you're organizing data, you run smack into this massive dilemma. What's more important, being able to find any single item in a split second, or being able to easily add, remove, and shuffle things around whenever you feel like it? The tough part is you can't always have both. And this one choice, it has a huge impact on how all our software works. So, I want you to really think about that for a second. If you were the one building an app, which would you prioritize? Instant, lightning-fast access, or total flexibility? This question, right here, is the core reason we have so many different ways to store data. And that dilemma brings us to these two classic approaches. On one side, you've got arrays. Think of them like a perfectly ordered row of mailboxes, all connected, all in one line. On the other side, you have something called a linked list, which is way more like a treasure hunt, where each item just gives you a clue to find the next one. For today, we're zeroing in on those mailboxes, the array.
So, what is it about an array that makes it so special? Let's pop the hood and see why this structure is the absolute champion of fast access. And, spoiler alert, it's all about how it uses the computer's memory.
So, when you get right down to it, what is an array? Well, you can think of it as a container with two really strict rules. First, all the items inside have to be the same type. And second, they all have to live together in one single unbroken line in the computer's memory. And the most important rule of all, to find anything, you just need its address, or index. And in programming, we always start counting from 0, not 1. That first spot is always index 0. And this continuous block of memory is where the magic really happens. Because everything is in a predictable line, the computer can do some super simple math to instantly jump to any item just by knowing its index. It doesn't have to search at all. But that rigid structure is also its greatest weakness. The size is fixed from the start, so if you run out of space, you can't just tack on an extra room. No, you have to find a bigger plot of land, build a whole new, bigger house, and then move every single item from the old house to the new one. Now, this is actually how most modern programming languages get around that fixed size problem. They give us something that feels flexible, often called a dynamic array or a list. You can just keep adding stuff, and it feels like it grows magically. But behind the scenes, whenever it runs out of space, it's doing that exact moving house operation for you. It secretly finds a bigger block of memory and copies everything over. It's a fantastic trick, but that copying process isn't free. It has a performance cost. And that moving house cost is just one piece of a bigger puzzle. You see, arrays are fantastic for reading data. But what happens when you want to change something right in the middle of that perfect continuous line? Well, this is where the array's biggest weakness, its Achilles heel, really shows up. At the end of the day, it all boils down to one simple, unavoidable fact. The biggest performance problem for an array isn't reading data. It's the shuffling. It's all the work that has to happen whenever you insert or delete something that's not at the very end. Let's watch this in slow motion. Okay, so we want to stick the number 99 in at index 2, but there's no room. So what do? We have to grab the 40 and slide it one spot to the right. Then we have to grab the 30 and slide it one spot to the right. And finally, we have a gap where we can drop in our 99. You see that domino effect? That's what computer scientists call an O of n operation. It's a fancy way of saying that the amount of work grows in direct proportion to n, the number of items you have to shift. And guess what? It's the exact same story for deletion. To get rid of the number 5, we can't just leave an empty hole in our perfect line of mailboxes. That's illegal. So we have to take everything that came after it and pull it one step to the left to close that gap. Once again, the amount of work depends entirely on how many items we had to shuffle. It's another O and N operation. Okay, so we know how to access things if we know their index, and we know it's expensive to change things in the middle. But what if you don't know the index? What if you're just looking for a specific value, like the number 9? Well, this is where we launch a search mission. And we've got two main ways to do this. The first is the one you'd probably think of first, a linear search. You just start at the beginning and check every single box, one by one, until you find what you're looking for. It's simple, but man, it can be slow. But if your array is sorted, you can unleash a superpower called binary search. It's way, way faster, but it has one non-negotiable rule. The data has to be in order first. Let's see just how mind-blowingly powerful binary search is. We're looking for 9. Instead of starting at the beginning, we jump straight to the middle. The middle item is 7. Now, because we know the array is sorted and we know our number, 9, is bigger than 7, we can instantly throw away the entire first half of the array. We didn't even have to look at it. Now, we just look at what's left, find its middle, and boom, there's our 9. It is so ridiculously efficient. All right, we've covered a lot of ground, from how arrays are built to how we find things in them, so let's boil this all down into a super practical guide. Think of this as your go-to cheat sheet for understanding when an array is the right tool for the job. And really, it all comes down to this table. Look at that top line. Accessing an item by its index is O of 1. In plain English, that means it is always instantly fast. It doesn't matter if the array has 10 items or 10 million. But then look at the middle. Inserting, deleting, or doing a simple search is O of n. That means the task gets slower and slower the bigger the array gets. And then you have the superstar, binary search, which is O of log n. That means it's so efficient that it barely slows down at all, even for gigantic arrays. This table right here tells the entire story. You get that amazing O of 1 instant access, but you pay a potential O of n penalty for flexibility. So now you have the tools to see this trade-off everywhere. The next time your photo gallery loads in the blink of an eye, you're seeing the power of O1 access. And if you've ever deleted a song from the middle of a huge playlist and the app just freezes for a split second, you are literally feeling the cost of that ON shuffling operation. Now that you know the rules, where else do you see this battle between raw speed and easy flexibility playing out in the tech you use every single day?